Last section for chapter 3, which is 3.5, which is patterns of the ionization energies on the periodic table. So kind of what we talked about already, but more in depth. So you can see here the ionization energies between a row, lithium through neon. We talked about a little bit about beryllium and boron and nitrogen, oxygen, why their ionizations dip a little bit, and we'll go into that today. So why does the ionization energy increase as you go across the periodic table? A few things. First, the force of the attraction increases. You have more protons and electrons, so there's a greater attraction between the electrons and protons that requires more energy to remove that electron. The nuclear charge increases, that's because of the number of protons. And the distance between the nucleus and the outer electrons actually stay pretty constant because it's the same quantum shell, same energy level. And then shielding by the inner electrons are the same, meaning the first energy level or the second energy level, where the electrons are being shielded, is remaining constant. Alright, what about the dip that goes way down after helium and lithium, or neon and sodium? So you have helium goes to lithium, is a huge drop in ionization energy, and this deals with a couple things. So why does the energy increase or energy decrease as you go from the end one period to the beginning of another? So the larger radius, you're going to another quantum level. So larger radius means the electrons are further away from the protons, so that means you can remove that electron more easily. Distance between the nucleus and outer shell increases. The shielding by inner electrons increases, so there's the force that are holding the inner electrons is strong, so the outer one is easier removed. And that outweighs the increase in nuclear charge. So even though you have more protons, the distance between those protons and the outer electron is larger, so there's less force holding on to that electron, so it's easily removed. Alright, the dip between beryllium and boron and nitrogen and oxygen. We talked about this on Tuesday, that there is the electrons and the orbitals is specific to this dip. So between beryllium and boron and nitrogen and oxygen, why does the ionization energy dip between these elements? Look at the electron configuration. Beryllium is 1s2, 2s2, and boron is 1s2, 2s2, and 2p1. So since it goes to the p orbital, boron, the distance actually increases just a little bit from the nucleus, so it's a little further away. Plus the s orbital is full in the beryllium, so it's more content or more stable than the 2p1 or 2p orbital, where that has one electron. So it's a slight decrease. When you add a subshell like the 2p, it's a little further away from the nucleus, so it has less electron attraction. It's attracted to the electron less because the distance. Shielding is still the same. It increases because of the inner electrons, and again, it outweighs the increase in protons because of that distance, and it's in the 2p or in the p subshell than the s or subshell. You look at nitrogen, we talked about this. It has a positive spin all the way across. Oxygen has the same as nitrogen, but you have that negative spin down. So electron is removed from the same orbital, but the spin plays a role because of the pair in the 2p x, y, or z orbital in oxygen. So this one is more difficult to remove because it has a full 2p positive spin, and this electron is more easily removed because of the distance they're pushing against. They're pushing against each other because they're both negative. So why does the extra repulsion between the paired electrons mean for ionization? It means that less energy is needed to remove because they're repulsing each other. They're repelling each other, sorry, repelling. Alright, period 3 follows the same as period 2. The D block plays a different pattern based on their filling of the D orbital. But generally, you're talking about an increase in ionization across and an increase going from the bottom to top. Alright, so to talk about going down a period, the ionization energy actually decreases. And really one reason why is the distance. It's very easily removed. Even though your protons are increasing, you're going to a different energy level, so the radius of the atom is actually increasing, so the distance between the protons and the outer electrons are greater. Alright, homework question is to look at these ionization energies of sodium, magnesium, aluminum, and silicon and explain the general increase in ionization energies from sodium to lithium general, and then explain why aluminum has a lower first ionization energy than magnesium. And then question B, the first ionization energy of fluorine is 1680 kilojoules per mole, and iodine is at 1010 kilojoules per mole. Explain why fluorine has a higher first ionization energy than iodine despite having a smaller nuclear charge, smaller protons. Alright, that does it for chapter 3. Any questions?